All right, welcome. Today, we're digging into the physics behind literally everything that spins. I'm talking a planet in orbit, a top on the floor, a figure skater doing a pirouette. It's all governed by this one idea called moment of inertia. And once you get that, you get the secret to spin itself.
You know, you already get this on some level. Trying to push a heavy box across the floor? It's tough. Its mass makes it, well, stubborn. But what makes something stubborn to spin? It's not just how heavy it is, there's something else going on. So what's that missing piece of the puzzle?
So let's break down these two different kinds of stubbornness. In physics, that resistance to being pushed in a straight line is just called inertia. But that resistance to being spun around, that's a whole different ballgame.
And yeah, physicists have a fancy name for this rotational stubbornness. It's called the moment of inertia, and we usually just write it as the letter I. It's pretty simple when you think about it. It's just a measure of how much an object fights you when you try to spin it.
This right here, this is the core idea. You need to lock this in. Just like mass is the measure of an object's resistance to being pushed straight, moment of inertia is the measure of its resistance to being spun. They're basically twins, one for straight lines, one for circles.
Okay, so if this moment of inertia thing is so important, what actually makes it up? Let's pop the hood and look at the recipe for what makes something hard to spin. Whoa, okay, I know what you're thinking. That formula looks pretty intense. But don't worry about the weird symbols for a minute. Just think of it like a recipe. And the cool thing is, it really only has two main ingredients that decide how hard it is to spin something.
And here they are. First up is m, which is just the object's mass. You know, how heavy it is. Easy enough. But the second ingredient, r, that's the one you gotta watch. That's the distance of that mass from the center of the spin. And as you're about to see, that distance is a huge deal.
So this brings up the most important question of all, right? You've got two ingredients, how heavy something is and where that heaviness is located. Which one do you think has a bigger say in making something hard to spin?
And the answer is distance, and is not even close. The location of the mass isn't just a little more important, it's exponentially more important. Why? Because its effect is squared. That means if you double the distance of the mass from the center, you don't just double its resistance to spin, you quadruple it.
Now, because distance has this incredible powerful effect, it means that an object's shape is, well, it's everything. Let's see how just changing the shape and where the mass is completely changes the game.
I want you to picture a thin ring, like a hula hoop. This is the perfect example of this whole idea in action. And why is that? Because for a hula hoop, all of its mass is pushed out as far as it can possibly get from the center. This design gives the ring the biggest possible moment of inertia for its weight and size. It makes it the most rotationally stubborn, simple shape there is. And look at its formula. It's just mr squared. See how there's no fraction out in front watering it down? That's maximum stubbornness right there.
Now check out what happens when we start messing with the shape. For a solid disk where the mass is spread out evenly, the moment of inertia gets cut in half. It's half mr squared. Now look at a solid sphere, where even more of that mass is packed in close to the middle. It drops all the way down to just 2/5 mr squared.
And that right there is the whole point. A smaller fraction means less rotational stubbornness. It means it's easier to spin. This is exactly why a solid bowling ball is way easier to get spinning than a giant hula hoop that weighs the exact same amount.
So, let's wrap this all up. What's the one big, crucial idea you should walk away with after all of this?
We've seen that the key factor is always how the mass is spread out. And yeah, it's good to know the technical stuff, that it's always a positive number, that it's measured in kilogram meters squared, but honestly, the real magic isn't in the units.
But look, if you remember just one thing from all this, make it this. Moment of inertia isn't really about how heavy something is. It's about where that heaviness is located. The distribution of mass, amplified by the square of its distance from the spin, that's everything. And this is exactly why a figure skater pulls their arms in tight for that incredible final spin. They're not getting lighter. They're pulling their mass closer to their center, which crashes their moment of inertia. That makes their rotation speed up like crazy. It's not magic. It's just physics. And now, you see it everywhere.